Okay. So, in the last lecture, we have seen one of the most important result in this subject, namely if f is Riemann integrable to pi periodic function, then norm of f minus of S n f to norm, this goes to 0 as n goes to infinity, and what we have seen is that n varies over z, which means n is from minus infinity to infinity. Mod of f hat of n square is equal to, which, just to recall, the square is minus pi to pi mod of f of x square dx. So, as an application of this, what we have seen, also one application, that is the another proof of Riemann-Lebesgue lemma, that is, if f is a Riemann integrable function, then f hat of n goes to 0 as mod n goes to infinity. What this is saying is that if f is Riemann integrable, then the sequence f hat n is square summable. So, it is natural to ask that if we have any arbitrary square summable sequence, is it necessarily true that there exists a Riemann integrable function f for which f hat of n is equal to that sequence? This question will address little later. So, today let us see some more application of this beautiful result. As we have seen earlier, if we give smoothness to the function, then the Fourier coefficient, it decreases. It has if f is C k minus pi to pi, then what we have seen is less or equal to some constants by mod n to the power k. So, this tells us that if f is C 2 or C 3, then the Fourier series of f converges absolutely pointwise. But now, natural question is that if f is only in C 1, then this result is going to give us that f hat of n is less or equal to some constant times 1 over mod n, and that is not a convergent series. So, we may not get absolute convergence just with this decay of f being in C 1. But now, if we apply this result, this is the Parseval identity, or Parseval theorem. This identity is called the Parseval identity, and by using that, what we are going to see is corollary if f belongs to C 1 minus pi to pi, then S n f converges to f pointwise here. So, the proof is f is in C 1. So, observe that f prime exists and is a continuous function, hence Riemann integrable, being f being in C 1. So, f prime hat of n, we have seen that this is minus of I n f hat of n. Okay. So, now if I look at summation over n from minus infinity to infinity mod of f hat of n is equal to, I can write it f hat of 0 plus mod n greater or equal to 1 mod of f hat of n, which is equal to mod of f hat of 0 plus summation over mod of n greater or equal to n. What I will do is here 1 by n I will multiply, then I have f hat of n mod. So, now this is nothing but f hat at 0 plus summation over mod n greater or equal to 1 over mod n, and then this is f prime hat at n mod. Now, this by using the Cauchy-Schwarz inequality, we get that this is less or equal to f hat at 0 plus summation over mod n greater or equal to 1 by mod n square whole to the power 1 by 2 into summation over mod n greater or equal to 1 mod of f prime hat of n square whole to the power 1. This is Cauchy-Schwarz inequality. So, now this is dominated by f hat of 0, which is some finite number 1 by n square. We know this is a finite number, the series converges, let us say some a, and now this I can change this sum to n varies over z. And which essentially this is nothing but this, the last term is f prime of 2 norm, which is finite because it is a continuous function. So, this is finite, therefore, the Fourier series converges absolutely. Hence, by Fair theorem, S and F converges to F for all x. In fact, the convergence is uniform. Okay. So, this is in fact, this historically this theorem was proved by Dirichlet without using this. So, that there you can now one can see from the basic principle one can prove this result. Okay. So, now some other applications. Now, let f of theta is equal to mod theta on minus pi to pi, and which is 2 pi periodic. So, we can calculate Fourier coefficient, let us say n not equal to 0, f hat of n, if we compute this by definition, and which is 1 by 2 pi. If I do this as minus pi to 0 plus 0 to pi, Then here I have got minus of theta e to the power minus of I n theta, and here theta e to the power I n theta d theta. So, we can compute this by integration by parts. So, no, we can still make little simplify this. If in the first integral, if I make a change of variable theta going to minus theta, so what I am going to get is that this is 0 to pi theta e to the power I theta times theta e to the power I n theta d theta, and plus 0 to pi e to the power minus of I n theta d theta, which is equal to 1 by 2 pi. This is 0 to pi theta cos n theta d theta, and then there is a factor of 2 e to the power I n plus e to the power minus of I n. This is going to give me 2 cos n theta. So, now it is easy to compute this integral. So, this is 1 over pi, and then this is if I have put the theta, then this is the integral of this is sin n theta by n. This is 0 to pi minus integral 0 to pi sin n theta d theta. Now, this is equal to at sin n pi is 0, sin 0 is 0. So, that first term vanishes, and now I have a second minus, but now sin theta is cos, here there is a factor of 1 by n is missing. So, this is cos n theta by n square, and then this is 0 to pi. This is equal to 1 by pi n square, and then minus 1 to the power n minus of 1. Now, if n is even, then f hat of n is equal to 0. Now, if n odd, then this is equal to, this is minus of 1, this is minus 1, which is equal to f hat of n is going to be minus 2 by pi n square. Okay. And easily one can compute f hat at 0. This is equal to 1 by pi, this is an even function. So, this is 0 to pi theta d theta, which is equal to pi by 2. Now, once we have that, then what one can see is by Percival identity, norm of f square is equal to summation over n varies over z mod of f hat of n square. We are preferring to write a subscript 2 here. Okay. So, now what is the left hand side? Norm of f 2 square, this is equal to 1 by 2 pi, then this is minus pi to pi mod of f of theta square d theta, which is equal to theta square. So, this is 1 by pi 0 to pi theta square d theta, which is equal to 1 by pi theta cube by 3 0 to pi, which is equal to 1 over pi cube by 3, this is equal to pi square by 3. So, therefore, norm of f, therefore, pi square by 3, this is equal to this thing, this we have calculated. So, f hat of 0 is what we have calculated is pi by 2. So, this is pi square by 4 and plus this is one, as we have seen, is that this is if n is odd, then this 2 by pi n square. So, this is going to be equal to 2 times summation over n odd and n greater or equal to 1 4 by pi square n to the power 4. So far so good. So, now this will imply this is 2 n plus 1. If I take, then what we are going to get, this is pi square by 12. This is equal to 8 by pi square summation over n is equal to 0 to infinity 1 by 2 n plus 1 to the power 4. So, this implies that summation over n equal to 0 to infinity 1 by 2 n plus 1 to the power 4, this is equal to pi square by 96. Yes. And now, summation over n equal to 1 to infinity 1 by n to the power 4, this is equal to summation n even plus n odd. So, which means this is equal to, if I take this n even, which means n equal to 0 to 1 to infinity, 1 by 2 n means 2 to the power 4 is 16 n to the power 4 plus odd is n equal to 0 to infinity 1 by 2 n plus 1 to the power 4. So, we know the value of this. So, now if I bring it to this side, so which is going to be 15 by 16 summation over n from 1 to infinity 1 by n to the power 4, this is equal to, we have got pi square by 96. So, this implies that summation over n 1 to infinity 1 by n to the power 4, oh sorry, this is pi 4. I have made a mistake over here. When it goes to this side, I will get a 4 here, pi to the power 4. So, this is pi to the power 4 and therefore, this is equal to pi to the power 4 by 90. So, we have seen that we have earlier we have calculated the series n equal to 1 to infinity 1 by n square, that we have computed and we have found that that is pi square by 6. Now, again we can compute the series summation over n from 1 to infinity 1 by n to the power 4, which is equal to pi 4 to the power 4 by 90. In the similar way, so if we define example 2, so consider two pi periodic odd function which is defined by f of theta is equal to theta into pi minus theta on where theta varies from 0 to pi, and so this you do this odd extension, this if this is there, the odd extension is from minus pi to pi. So, if you compute the Fourier coefficient, then you will find that this Fourier series, this is the simple calculation. So, I am not going to repeat those calculation. Fourier series is given by summation over n odd function. So, sine series is going to survive. So, this is sine n theta by n cube, and I will get a factor of 8 by pi. So, this one can write it down to be equal to minus of I 2 sin theta. If I take, then this is 4 divided by pi, and n odd n greater or equal to 1 e to the power I n theta minus e to the power minus of I n theta divided by n cube. Again, by using the Parseval identity, what we are going to get is that n odd means 2 n plus 1, and the square is 2 n plus 1 to the power 6, the n to the power 6. So, this right hand side is going to be equal to the square of this is 32 by pi square summation over n from 0 to infinity 1 by 2 n plus 1 to the power 6. This is f hat of n little l 2 norm. So, this should be equal to 1 by 2 pi minus 0 to pi theta square into pi minus theta square d theta. This computation would be easy, and you will find that this is going to be pi to the power 4 divided by 30. So, therefore, this will imply summation over n equal to 0 to infinity 1 by 2 n plus 1 to the power 6 is equal to pi to the power 6 by, so this is 960. Okay. So, once we have that, then we want to compute n equal to 1 to infinity 1 by n to the power 6. Again, by breaking it into even and odd, and we know the value with the odd 2 n plus 1. So, this what we can get is essentially this is 2 n means 1 by 64 summation over n equal to 1 to infinity 1 by n to the power 6 plus summation over n equal to 0 to infinity 1 by 2 n plus 1 to the power 6. So, this implies that 63 by 64 summation n equal to 1 to infinity 1 by n to the power 6, which is equal to this value we know, this is pi 6 by 960. So, this implies summation n equal to 1 to infinity 1 by n to the power 6 is equal to pi 6 by 945. So, now here we have found the series 1 by n square, 1 by n 4, 1 by n 6. So, it is natural to ask that whether one can find the series, can sum up the series 1 by n to the power 2 k. As a matter of fact, one can do that, not as easy as this. However, for the odd power 1 by n cube, or 1 by n to the power 5, this is all this which is not unknown, and it is a very very hard problem to find the value with odd power. Okay. So, another very beautiful application of the Riemann-Lebesgue lemma is to compute the integral, which is well known, and all of us we have used it several times. This is sin x by x dx. So, what is the value of integral 0 to infinity sin x by x dx? So, this we know that this is pi by 2. There are several ways one can prove this identity. So, we will see by using the Fourier analysis technique how we are going to prove this identity. Okay. So, let us have a closer look at this. So, what is the left hand side? 0 to infinity, this is sin x by x dx. This I can write that this is limit n goes to infinity 0 to n pi sin x by x dx. This is that is what we would like to compute. So, this is also I can make a change of variable n, or I can take n plus 1/2 of pi, because sin n plus 1/2 appears in the Dirichlet kernel. So, that is why I am making it n plus 1/2. So, now if I make of change of variable, so then this is going to be 0 to pi sin n plus 1/2 of x, and then dx by x is not going to change. So, this is what we will get, and we have limit n goes to infinity. So, this is so now what we know? We know that instead of this, if we have minus pi to pi sin n plus 1/2 of x by sin x by 2 dx. This we know, this is the Dirichlet kernel. So, 1 over 2 pi of the Dirichlet kernel, this is 1. So, this is going to be 2 pi. So, now instead of x in the denominator, if we have sin x by 2, then our life is simple. So, therefore, what it suggests is that suppose now 1 by sin x by 2, I can write it 1 by sin x by 2 minus 2 by x plus 2 by x. And then if we look at, if we define f of x, this is equal to 1 by sin x by 2 minus 2 by x, as we can see that this converges to 0 as x goes to 0. Just you can do it various ways, just apply the L'Hopital rule, and then you can get that this converges to 0 as x goes to 0. So, now this is a well behaved function. So, using this, in the next lecture we are going to compute the integral 0 to infinity sin x by x dx. Thank you.